Today we're going to see how to build a high-pass filter on a breadboard and how to measure its cutoff frequency. This is a circuit diagram for the high-pass filter. So let's see how we can build this circuit on a breadboard. I'm going to start with the capacitor up here. We see that one leg of the capacitor is attached to A1, this analog output, and we're going to be using a 10 microfarad capacitor. So let's find that 10 microfarad capacitor and put one leg into A1. Here's my 10 microfarad capacitor. I'm going to put this capacitor into the board. I'm going to put one leg of the capacitor into A1, the same row as the A1 pin. I'm going to put the other leg into some other row down here in the middle of my board. I'm also going to turn the power off now by pushing this little button up here. That just makes it a little bit safer for me to put things into this board. That way, if I accidentally touch power to ground, it doesn't cause a short. Here's our circuit diagram. We've attached our capacitor to A1. Now the next thing that we're going to do is we're going to attach this 1 kilo ohm resistor from the capacitor to ground. I'm going to push one leg of that into the same row as this capacitor, and I'm going to push the other leg of the resistor into ground down here, this long row along the bottom of the breadboard. All right, now I have attached my resistor. The last thing that this diagram shows is that there's a connection from this junction between the capacitor and the resistor over to channel 2. I'm going to make that connection using a jumper wire. So I'm going to take this jumper wire. I'm going to put one end into the junction between the resistor and the capacitor. And I'm going to push the other end of the wire into channel 2. Okay, so now I've made that connection. Now we can take a look at what we see on the screen. So here we are in the Enscope software. The display shows that the Enscope is asleep. So the first thing I'm going to do is I'm going to turn the Enscope on by pushing that little white button on the Enscope board. Now the Enscope is on. Now what I'd like to do is I'd like to turn on channel 1. This is our output. And then remember that that output is being connected to channel 2 on the input. So I'm going to turn on channel 2 as well. So I've got analog 1 out and channel 2 on to measure the result. I'm going to adjust analog 1 so that I'm using 4.75 volts. And I'm also going to make this bipolar. So that should be a signal that's 4.75 volts peak, and that should be going into my circuit. And then we're measuring the output here on the screen. We can see that the output is considerably less than 4.75 volts. But what we'd like to do is we'd like to see the input here as well. So in order to see the input, I'm going to go back to the breadboard and I'm going to wire directly from A1 over to channel 3 so that I can see what the input voltage looks like. So here's my circuit. I'm going to turn the power off just to be safe. I'm going to add a wire that goes from analog 1 over to channel 3. And this will allow me to see the output from channel 1, analog 1, directly on channel 3. I'm going to turn this board back on so that I can see it on the screen again. Now that I've connected analog 1 to channel 3, I'm going to turn channel 3 on here so that I can see it. So we can see that the input to our circuit is much larger than the output to our circuit. This is because we have a high pass filter and we're putting in a low frequency. So a lot of our signal is being absorbed or attenuated by our circuit. Let's see what happens when we increase the frequency. So as the frequency goes up, you can see that less of the signal is attenuated. It'll go up a little bit higher. Now it's getting a little bit hard to see what's going on, so we'll adjust our time per division. Now you can see that the green output signal is much larger than it was before because this is a higher frequency. And if we go up even higher and adjust our scale again, and we can turn off channel 1 because we're not really using that. Now the input and the output are virtually identical, so they're sitting right on top of each other, so it's hard to tell which is which. We can turn on triggering on channel 3 and maybe zoom in a little bit more and see if we can see this a little better. When we zoom in a lot, we can see that the signals are not quite identical, but they're very, very close to each other. So we can see that at low frequencies, this high-pass filter absorbs most of the incoming signal, and at high frequencies, the incoming signal can pass through unimpeded. But what we really care about here is we care about that cutoff frequency, that point where we kind of go from absorbing most of the signal to letting the signal go through. So what we really want to do is we want to measure where that point is. The way that we measure that is we adjust our frequency until the output is at 70% of the input. Okay. Now, we can see on the screen when the output goes up and down, but there's not a real clear marker on our screen to tell us where 70% is. So I would like to create a voltage that we can use as a reference so that we know what 70% of our input is. So we can use a voltage divider circuit to create that reference. Here is a voltage divider circuit that we're going to build, and that will give us about 70% of our input signal. So we're going to create a voltage divider with a 15 kilo ohm resistor and a 24 kilo ohm resistor, going from 5 volts to ground, and we're going to connect the middle point there to channel 1. So let's do that. First thing we're going to do is we're going to attach this 15 kilo ohm resistor between 5 volts and channel 1. So let's do that. This is a 15 kilo ohm resistor, so I'm going to attach that from 5 volts to channel 1. I'm going to push one end into this 5 volt row, then the other end is going to go into the channel 1 row. Okay, that's the first connection. Now this diagram shows a 24 kilo ohm resistor going from channel 1 to ground. So I'm going to add that resistor. Okay, so now I've made that connection. So that should now create a reference voltage here on channel 1. So I'm going to turn the Enscope back on, and we can look back at our Enscope software. So there's the Enscope software. I'm going to turn channel 1 on now because our reference voltage is on channel 1. And there is our reference voltage. So what we want to do now is we want to adjust our frequency until the output signal is just about hitting that reference voltage. The top of our output signal should just about be at that reference voltage. So let's do that. So we'll go down a bit. Not really there yet. Go down a bit more. Now it's getting a little bit hard to see our signal, so I'm going to adjust our time scale. So we can see that the output signal in green here is starting to diminish, but it's not down to our reference level yet. So we have to keep lowering our frequency. Oh, and we're just about there. So that's at 15.85 hertz. So I'm going to right click on here and enter another value. I'm going to type in 15, and that puts us just about right on target. So at 15 hertz, our output voltage drops to about 70% of our input voltage. That means 15 hertz is the cutoff frequency for this filter. In other words, signals below 15 hertz mostly get absorbed, and signals above 15 hertz mostly pass through this filter unimpeded. So that's how we measure our cutoff frequency on a circuit board. We build the circuit, we put a sine wave into the circuit, and then we find the frequency of that sine wave where the output drops to 70.7% of our input. And that frequency where the output drops to 70% is our cutoff frequency.